Hello and welcome to today's Australian Water School webinar titled Let's Get Physical. Today we'll be talking about physical hydraulic models, when you need them, why you might need them, and how to use them. And yes, that webinar title is a nod to our very own adopted Australian, the late Olivia Newton-John. Speaking of Australia, we have got quite a few attendees from down under with us today, but we've also got a huge number of participants from right around the world. So thanks so much to our global audience for joining us today. Now, as we welcome our presenters, Morten Kramer and Ben Modra, as you turn your cameras on, I've actually turned off my own fake background today to show what's really behind me in every webinar, which is a whole wall of Legos. Now, coming to us today from the land of Legos will be Morten Kramer, who will step us through some really cool models and hit some of the underlying principles during our tour. So Morten, if you could let us know a little bit about where you work and how long you've been doing what you do.
Yeah, hello, I'm Morten Kramer. I live in Denmark and I've worked with engineering challenges related to wave structure interaction for the last 25 years. I'm working part-time at Aalborg University as an associate professor and part-time for the private company Floating Power Plant. I'm looking very much forward to this event. Thanks.
All right, well, it's good to hear from you. Now, Ben has been with us on quite a few previous webinars. Ben, let us know what you'll be talking to us about today.
G'day, Craig. I'll be talking about physical modelling across coastal and hydraulic structures, and really how you interface, how people can come and engage us and what they can expect from a physical model.
Thanks for that, Ben and Morten. We will share some content from our third presenter, Sarah McEwen, momentarily. But in the meantime, I wanted to just ask a quick question leading into some of the content. This is just for fun, but it does require a little bit of algebra. If you were to film a wave tank at Lego scale, how much should you change the video speed to make it realistic? So I've got this Lego ship here, this sailing vessel, and I've got my minifigure. If you were to model this and put it in a basin that's at the same scale as that minifigure, what would you have to do to the video? Would you need to speed it up, slow it down 3 times, 5 times, 7 times, faster, slower? Have a think about that. It requires a little bit of algebra, but we want to prepare you that the answer is coming in Morten's presentation. If you want to keep watching, find that answer and try to work it out yourself. We've also compiled all sorts of background resources for you at a website called hydroschool.org/physical, and we will share those links with you at the end of the presentation today. Now, Ben and Morten are dropping into the background to address your Q&A questions while we take our first guided tour of the day. Now, this one's going to involve a very special treat with a bit of a history lesson about physical modeling. So let's roll the clip. All right, we're lucky to be joined by Sarah here, who is the secretary of a nonprofit responsible for the care and maintenance of the largest physical model in the world. So what can you tell us about this one, Sarah?
So we'll talk a little bit about what flooding history led to the Army Corps decisions and funding to build this model, how the model was constructed, some of the simulations that were the mission for the Army Corps, what's been happening since it was retired, and then a little bit about what the nonprofit is doing to restore and increase access to this site. So in 1927, we had a pretty devastating flood. It caused the levees along the main line to fail. So for several months, people were seen camping on these roads and these levees, and it was an entirely devastating economic event. So as a response to that, in 1928, Congress passed the Flood Control Act, which gave authority funding not only for new hydraulic structures, increased looks at the levee heights, but also funding into research and development into how we prevent these events in the future, how do we analyze these, how do we anticipate these types of events. So from that funding and appropriation, the Army Corps wanted to build a physical model. It was Major General Eugene Raybold's idea. He was the chief of the engineer of the Army Corps at the time. So he had this vision that he wanted to build a physical model that represented the entire basin of the Mississippi River and tributary system. As they got into it, 1942 was about when, from 1928 to 1942 was when they finally got all their ducks in a row. So they started planning for construction. They purchased the land for a prisoner of war camp, and they purchased the land for this physical model. The reason being is, 1942, we're in the middle of World War II. The labor source is not readily available to do the construction needed for this research activity. Since it wasn't a war-directed activity, it was a labor source that could be utilized for that action. So they purchased all of this land. They built our prisoner of war camp. They utilized the prisoners of war to do all of the earthwork and subsurface grading. If you come and visit us out at the site, anything that is brick was hand placed by a prisoner of war. So all of the underground cisterns, all of the subsurface returns, all of the rerouting of the channel, all of that was done by the prisoners of war. So about 1943, they finally start construction on this process to do like the grading and the rerouting and getting everything kind of together. Here's what the camp looked like. They mostly had engineers from Northern Africa conflict that were placed at this prisoner of war camp. So this is the camp and what it would have looked like at that time. This is kind of during the process of construction. On the left, you can see engineers doing survey on horseback. On the right, you can see everything was done by hand with just picks and shovels and wheelbarrows, and they rerouted Baker's Creek to the south so they could have the land space available for the physical model. The value of this labor at the time of 2017 would have been 14 million. But several years ago, the city of Clinton, which is really close to this park, hosted a reunion of the prisoners of war to come back and see the model while it was still kind of in operation. So how was it constructed? Once all of the grading was accomplished, they kind of had two different methods to develop these concrete panels. And these concrete panels are roughly 10 by 10 feet. They took the 1944 quad maps, they laid them out on the ground, and initially they did the template method. So think HECRAS 1D cross sections. You have two cross sections that were surveyed, and then they would interpolate with concrete between those two metal cross sections. Later on, especially when you got into the lower, flatter terrain, especially in the deltas, they needed more detail and more preciseness in how they were developing. So what you can see in the top picture is they would lay out the quad maps, they would trace the 10-foot contours with wire ribboning, then they would scale up that wire ribboning into the form of the panel, and then they would hand place concrete between all of those wire ribboning to get the shapes of the panels. Again, this is like a giant art Lego piece out in the middle of this park because every panel is hand shaped. In the channel itself, where they had the symmetry and they wanted more detail between the wire ribboning, they would place little bolts, and that's how they got additional bathymetric data within the channel itself. But these are physical representations of the contours from the 1944 quad map. So it's as accurate as the 1944, but it is a fixed bed model. So once the panels were kind of constructed, we get into operation. As they got the panels upstream completed, they worked upstream to downstream so they could run some simulations, some calibration and validation on the upper reaches. And then eventually, when they completed the entirety of the model all the way to the Gulf of Mexico, they would run those full simulations. So they had 79 missions, and we'll kind of cover that in a second, that they would consider it to be a success. But early on, they were running verifications on the upper reaches. Initially, they wanted to do the entire river basin model. But the reality is the scaling can be different, especially in the headwater areas. So they ultimately dialed it back into just key confluence points where any backwater from the main line could be seen up into the reaches of the river and tributary system. So you can walk from the Gulf all the way up. Again, this is 1940s. This is, early 1950s. How are you going to model and, control 60 acres of concrete and run these different simulations on this massive scale? Initially, it was thought that it would take 30 to 40 people to run this model, pulling on the levers and everything to get it to go. But they used player piano technology and automation to run historic hydrographs through these different inflow controllers. There's 70 to 80 inflow controllers throughout the system that would pull water based on the player piano hole punch technology, ramp up the hydrograph, run it through a V-notch weir, and push out the flow to match those gauged beds. So they had inflow controllers that controlled how much water could enter the model at the different tributary and confluence points. They had stage transmitters that were at the same locations as the USGS gauges across the river basin model that had a probe at the bottom that would read the outflow stage. And then they had outflow returns and pulls throughout the system to pull out water to account for any losses that would naturally occur as you work your way downstream, and to handle the final outflow back into the pump and the sump system. And this is what the control house would have looked like. Every single one of those cylinders would have been a gauge location that was reporting out data on the stage and velocities at that location. And so they would read that, process that, and decide if that simulation was good, or run back out and adjust that simulation. This is what the player piano technology we're talking about. There was a perforated program roll that had the hydrograph built into it, and then they were able to control and manually switch and pump and run the inflow controllers. And here's what the inflow controller on the right as a whole system would have looked like. And then it would have pulled water, pushed water into that top of that tributary that you can kind of see proceeding from it. On the left is the stage transmitter. So that would have sat on what looks like a bridge. You can kind of see one in the picture, but at the bottom was the probe, and the probe head could vary up and down until it read the stage. But all of that was electronically submitted back to a control building. the goal of this model was to run 74 simulations. The Corps would have thought this was a success if it completed these 74 simulations. And a lot of them was historic verification of previous events. And once they calibrated and validated their models, as we all do with our numerical models and physical models today, they then started running some theoretical events. They wanted to run what happens if we have coinciding large events on like the Red River or, in the Ohio River Valley. How do we handle and manage the water in our river and tributary system along on the main line? Because that's a big economic driver for the U.S. How do we maintain that? How do we operate that? When do we make decisions on floodways? So they used all these simulations to help not only inform levee heights and how those levee heights may negatively or positively affect people up and downstream, but also how to make decisions on operating of floodways. So a couple of key simulations are listed here. The one that I'm most impressed by is that in 1969, they did a lot of testing to try to build their computer programs. So this physical model in this park in Jackson really led to a lot of the important research that ultimately went into the HEC, HEC2, HEC-RAS kind of modeling software that we use today. So to me, that's most important because that translates into my daily activities and what I do as a civil engineer in water resources. But so all of these simulations, it was fully operational from 1960 to 1966. They ran, those precursor upper tributary simulations before 1960. And then they ran, a couple of things after, the 1960s as additional tests became part of the question and wanted to do. But mostly it was pretty much done by 1973. So in the late 70s, different districts could rent or use or lease this property and run their own simulations. So the Memphis district of the Army Corps used the Memphis area and really played around with a couple of things. But post-models, kind of what we call that time after the simulations were done, in 1972, when all those goal simulations were done, all of the adjacent property was transferred to the Department of Interior, including the model itself. And then a lease was done between the Department of Interior and the Army Corps. But then in 1993, the Army Corps was really done with everything, so they gave the property to the city of Jackson. However, before they gave it to the city of Jackson, one last model was run. So the thinking, 1978 was really the last time this model was run until 1993. So within 48 hours, they had this model up and running. They wanted to run one more simulation. They wanted to look at the Burns Point, New Madrid floodway. And there was a lot of concern about, again, those coinciding really large events hitting at the same point. And they were worried about volume of flow at Cairo as well as Memphis. So they ran the operation of this floodway. They blew up the floodway to see, okay, if we do this, will this relieve and solve our problems and protect citizens in Memphis and Cairo? So this 1993 event was only done because the computer models that they were running at the time weren't able to give them results that they felt were physically representative of what was going to happen. Their computer models were they weren't giving them, as an engineer, we all have judgments. They just weren't making them feel super comfortable. So they wanted this physical model that they trusted to validate and kind of almost do a physical model informed 1D to assess the situation with the operation of the floodway. So they ran this, and as many of us in the US know, in 2011, we had severe high water and the floodway was actually operated. So this simulation and this physical model was a tool in the toolbox for the Corps to operate that floodway in 2011. So after 93, the property was given to the city of Jackson. Not a lot happened between 93 and 2016. In 2016, a group of engineers in Jackson, Mississippi kind of got together. We visited the site. We thought it was just too cool about to try to do something, try to increase understanding and just document the history of this park. So we formed a nonprofit. But to know what activities we're doing as a nonprofit, it's important to kind of get some aerial history on the park. So you can see in 2006, we have some trees developing. They no longer mow this park. And this is a little bit turned. This is looking north-south in model space, but it's actually, the west is on the bottom of the screen. It's tilted in a real world space. So you can see there's only a few trees. And then 2010, we get some more trees. 2015, some more trees. And then 2020, from 2016 to 2020, we clean up. So we increase access to these panels. We try to create a buffer. We cleaned up. But what also happened in 2020? COVID. So we weren't able to get out to the park for 2 years. But in the last year or so, we held the 80th anniversary celebration, and we've tried to get back out with more volunteers and increase access again to this incredible engineering landmark. I work with a nonprofit as my volunteer activity, besides being a hydraulic engineer by day. We give tours all the time. We have cleanup days the first Saturday of the month. If anybody's coming into town, let us know. We'd love to meet with you. But here's kind of what we hope to do. We hope to just preserve the site. We hope to increase access. We'd love to have trails in the shape of the states because that's kind of cool for kids to jump across state lines. And it really just shows this is a giant map. And then maybe restore a certain area for non-scientifically accurate simulations, but just be a really cool STEM resource for our community and our local high schools. So that's kind of our overview of the history of the site and how it was built. This was the original picture of what General Raybould wanted to have, and that would have been from the true headwaters all the way down to the Gulf.
Wow, well, that is fascinating. And so the future plans, are there going to be buildings on site, museums? Is it? I saw a couple of outlines there that might be structures. So is some of this going to be indoors then?
If you gave me all the money in the world and let me do this, I would have a science outreach center with a computer lab, maybe sponsored by Aquavay or somebody, we'll throw it out there. That could have, like, you go in the field, you see the physical model, you explore it, you understand hydrology, hydraulics, watersheds. Then you go into the computer lab and you see, this is how I could do it today. This is how the engineers do it today. And we can really do that connective piece and encouraging people to come into the field of engineering and really just watershed management. So, but we'd have boardwalks to try to get people not on the panels, but kind of just getting access to the panels. We would love to have, walking paths that are really accessible to all restroom facilities, and just to walk for scale, just to walk from Mississippi down at the bottom, you can see the shape of the states, to walk from Baton Rouge up to Memphis takes 30 minutes. This is 60 acres of concrete. All in all, it's 280 acres within the footprint of the model itself, like everything in that border. So it's massive. This could be a national landmark, a national park. It's really something that we're working towards, but we're not the owner. We're just doing what we can for the beautification.
Yeah. Wow. Well, you get a feel for the scale of that 30-minute walk from one end to the other. That is, the biggest hydraulic model or physical model in the world. And so in your daily life, so you're a civil engineer with Neil Schaefer, and so do you do any of this sort of physical modeling? I guess one of the questions that we have, that we're asking all of the panelists for our webinar, with all of the advances in hardware and software, does the future have a place for physical modeling? If so, why?
I have kind of a unique background. I was previously with AECOM, and they worked on the Mid-Barataria sediment diversion, and they had partners and team, and there was a lot of physical modeling done, especially for sediment transport components of that system. So I think projects specifically, if budgets allow, I think physical modeling is absolutely important for long-term assessment and impacts of what we're designing. Now, will the local DOTs run physical models? Usually not, because that's not necessarily needed. So I think it's just an answer of right sizing for the project, but there's going to be these large regional watershed, projects, even nationwide projects that need that physical modeling to make sure that we're accounting for all impacts from a variety of things, environmentally, flood, and future resiliency.
Wow. Well, yes, thanks for your expertise. Well said. I think that really summarizes everything that we're talking about with this topic on our webinar. And I'm glad to be able to represent this as, an icon of engineering and analysis. So thanks so much, Sarah, for being with us. All right, so hope you enjoyed that. Now, Sarah won't be able to join our live panel discussion due to the late hour in the U.S., but we'll definitely share some links to the Friends of the Mississippi River Basin model at the end of today's webinar. And you can use their contact form to get in touch with Sarah with any questions you might have about that fascinating model and that history. So now, over to Europe, where Morten is standing by live. Morten, if you can share your screen, let's hear a little bit about the floating power plant and what Lego minifigures can teach us about Froude scaling. So over to you.
Yeah, thank you, Craig. In this presentation, I'll show how small-scale experiments in a wave basin can be used to develop and improve calculation tools. For most new or innovative structures that are placed in the water offshore or nearshore, existing engineering tools are unreliable, and most importantly, the accuracy of the tools are unknown. Experiments in wave basins is a very useful tool for engineers, as reliable measurements of unknown or difficult physical processes can be made with very high precision. The tests I'll talk about in this presentation were performed recently in the wave basin at Aalborg University. I'll give two examples of how experiments are used for numerical model validation and calibration. The first example is for a sphere model. This case is part of an international research collaboration which focuses on improving hydrodynamic simulations models for wave energy devices. The second example is for the floating power plant. It's a floating wind turbine platform. I'll show how a calculation model based on the equation of motion can be calibrated using experiments. The facility at Aalborg University have multiple installations for hydrodynamic testing, but I'll talk merely about the wave basin. It's a somewhat small basin with an area of about 15 by 20 meters, which is appropriate for testing fairly small models at relatively shallow water depths. The wave basin is only a few years old and have the best state-of-the-art equipment and software. The basin is suitable for testing wave structure interaction effects with the following two cases as examples of that. The sphere cases consist of a number of different test cases where all measurements as well as simulation data will be publicly available. The dataset is intended to help engineers as a first step in validating their own hydrodynamic models for a very simple geometry, namely the sphere. The sphere is exposed to some very simple tests and the precision of different numerical models are evaluated. We have already completed a study with heave decay tests where all the results have been published and can be downloaded for free. The present case I will demonstrate in the next slide is for wave excitation forces. If you would like to know more about these sphere cases, please check out the supplementary material for this event. Numerical models of different fidelity have been used to simulate the forces on the sphere, which I will show now. The upper left video is a recording from the wave basin. The two animations on the right are for two different types of simulation models. The upper animation is the most advanced one using CFD with a so-called URANS model. The lower animation is for various types of models based on potential flow theory. The first one we see running now is for linear potential model LPF, which is a very simple and fast model. In the lower left plot, I've shown data from the experiments as well as the simulations. The upper one is for the wave, where we can see that this linear potential flow model, the orange curve, is deviating a bit from the measurements. We can see that the crest is not high enough and the trough is too deep. That's a limitation by that one. The two lower graphs here is the horizontal force and the vertical force. And we can see that the linear potential flow model is somewhat off, whereas the more advanced models predict the forces with higher accuracy. The weakly nonlinear potential flow model that was running over there before is including nonlinear Froude forces, and that gets a closer match to the reality. And the one that is running now, the fully nonlinear potential flow model, is getting very close to the exact results. The most accurate one is this advanced CFD model, which is a very complicated model, and it's time consuming to set up and run this. What is important to note here is that when we increase the fidelity, we get a closer match to the experiments, and we could see that the experiments were good to validate and assess the accuracy of these numerical models. The next example is for the floating power plant device. Floating Power Plant is a company which develops a floating platform for harvesting renewable energy offshore in large water depths, where fixed foundations of wind turbines is not economically feasible. The main part is a wind turbine, but the concept can be combined with wave energy and hydrogen storage. The floating platform will be placed in parks, as seen in the animation on the right. To validate and calibrate the numerical models used for designing the platform, we constructed a scale 1 to 50 model to be tested in the wave basin. We simplified the model by removing the moorings and the wind turbine. And we installed a force sensor on top of the model, which holds the model. And then we installed an actuator, which allows moving the platforms in various degrees of freedom. The scaling of 1 to 50 is visually seen by looking at the two small Lego men on top of the platform. They are 3.5 centimeters high, so in full scale they would be 175 centimeters high, approximately the same height as me. For experiments in wave basins, it's the gravity forces that dominate the physics, and scaling is performed using the Froude number. Froude scaling implies that the Froude number at model scale must be the same as the Froude number at full scale. Using this relation, it's possible to derive scaling factors for different parameters. For example, time will scale with the square root of the scaling. So at about the square root of 50 is about 7. So when we see a video from the wave basin, it will seem as time is running very fast. For this type of scaling to be true, friction forces must be negligible relative to the inertia forces. This is not entirely true, as in reality viscous force effects in the water, like turbulence, will somewhat affect the flow and the forces. If simulations are performed using a model based on potential flow theory, some correction is therefore needed. The motion of the structure is usually calculated based on a mathematical equation called the equation of motion, using inputs from linear potential wave theory. Let's look into that. Let's consider heave motion of the platform and vertical forces. I put on the forces acting on the platform. The pressure from the water on the hull is giving a hydrodynamic force. The mass of the device is giving a gravity force, and the restriction from above by the actuator is also applying the force. These forces can be put up in a force balance using Newton's second law. Force is equal to mass times acceleration. Using the formulation from linear potential flow theory, the forces are split up in contributions from wave excitation, wave radiation, and hydrostatics. But as I said, this formulation is not completely correct. So when we do simulations, we get a slightly different force compared to what we measure with the actuator. So we introduce a correction to account for nonlinear and viscous effects. So when we put that into the equation, we simply add that up. And in this way, when we solve the equations, all these special effects are accounted for in a very simple way. Now we have the forces on the platform. What is important to understand here is that the contribution to the force from the water is split up in different contributions, and then these contributions are simply added to form the total hydrodynamic force. In the following, I'll demonstrate how the small-scale physical setup with floating power plant is used together with this equation. We'll start out very simple with moving the platform by fast oscillations in air. In this case, we have only the gravity force and inertia force that will be measured with the actuator. And we can see that the inertia force will be proportional to the mass. On the upper plot, we see a time series of measured vertical accelerations and the forces measured by the actuator during the same time period. In the lower figure, I've shown all the measured data points as dots in this graph, where I have acceleration along the x-axis and forces by the actuator on the y-axis. We see that all the measurement points lie on a straight line with the slope matching the mass of the platform. So that's a nice little check. The next simple test is a hydrostatic test, where the water line relative to the model is changed slowly. The change is so slow that the acceleration is negligible and there are no radiated waves. This can be done either by moving the platform slowly, as I've done here on the top, or by draining or filling the basin slowly, as done here in the bottom. In similar way as the last slide, we have data here now for position and hydrostatic force, and they can be plotted up, the position versus force, as all these dots here. And in this way, we get the hydrostatic curve for the platform. By comparing to the calculations with linear and non-linear hydrostatics, we can validate the calculations. I bring up this example with two ways of doing the same experiments. Sometimes this is possible. In this example, it was possible to validate the full hydrostatic curve using change in water level, whereas the actuator was not strong enough to completely submerge the model. In the next type of test, we move the model with a constant speed in otherwise calm water. In the present example, we are moving the model upwards with a constant speed of 0.14 meters per second, which corresponds to 1 meter per second at full scale. The model scale test is very fast, so the video recordings from the lab is here played in slow motion by the factor 7 to visualize what it would look like in reality. In this case, we have merely a contribution from the hydrostatic part apart from the correction. The data from the actuator are compensated for the hydrostatic effect to get the correction force. And this correction is considered as a drag force, and it is taken as the mean value of the measurements during a time window where the response is fairly constant. In the following type of test, I put on incident waves, but I keep the platform fixed. In this case, we measure directly the wave excitation force on the platform. In the plots, I've shown the results of the on the vertical force and the moment here for the potential models before the corrections are included. In the middle plot, we see that all the models match quite well with the on the horizontal force without any corrections. But if we look into the moments, we see a clear difference. So from this, we see that these potential models could benefit by including some correction term. The procedure for calibration is further extended to include more components of the equation of motion. Here I've shown two further examples for radiation and a combined test. Validation and calibration is in practice done for a variety of situations, so physical configuration with various motion in different degrees of freedom, and changes in the environment like wave direction, wave period, and wave height. To conclude, we have seen that small-scale experiments is a good and reliable tool for validating and calibrating numerical models. Using the sphere test case, we saw that experiments were used in an international research project focusing on developing and improving simulation tools. The last example with floating power plant showed how dedicated experiments were used to verify and calibrate the simulation tools for this new type of floating platform concept. Thank you.
All right. Well, thanks so much, Morten. If you can go check the Q&A line now, there might be a few questions coming in that you could address in writing, and then we'll come back on with a panel discussion toward the end. So with that well underway now, Ben, if you can start sharing your screen, let's hear about some physical models right here in Australia. Over to you, Ben.
Thanks, Craig. And thanks, Morten. That was really interesting. Good deep dive into a couple of your models there. So common question, so this is really going back to the basics of hydraulic modeling. One of the comments that we get quite often is, why can't we do this with computers? Coastal modeling, or a model like this with a rock-rubble structure, is a really good example of the kind of challenges that you might have if you were trying to do it in a different way, with numerical modeling, for example. So in shallow water waves, as it comes into waves, as waves come into the shallow region, they become increasingly non-linear and complex. They shoal and they break. That can be quite hard to achieve in a numerical model. We've got a structure here with random placed units that are random shaped. You've got a combination of different units. This has got e-concrete units, which are ecological enhancement devices. So you've got different types of units. I can't imagine how you would characterize the flow through a structure, or how you would mesh a structure in between these rocks. So you've got the flow from above, flow through the rocks. You've got the interlocking of different units, and then you've got to sum all those forces together to characterize the release of a single unit out of the structure. And then once the first one's gone, then how do you go on and do following units after that? So there's quite a lot of complex things to capture, but in a physical model, we can do that relatively easily. So we physical model to reproduce the hydraulic processes, and we can do it over a long duration as well. It's quite easy to do long model runs. We can characterize the interactions between water and structures, and quite often it captures the unexpected, the things that we didn't really realize that might be an issue for our structures. For a project, this reduces risks and provides confidence, gives us an opportunity to optimize our designs and reduce cost. And it is in itself a cost-effective approach as a part of the design process, particularly if you can get it in early in your design process. So for coastal engineering, we look at wave transformation, the hydrodynamic loading, so the loading on structural elements like boardwalks or walls, seawalls, structure stability of rock or concrete army units. We look at overtopping, which is the safety for people on top of our structures and the infrastructure behind it, and erosion and sediment transport. For hydraulics, we're looking at flow conditions, particularly whether it's subcritical, supercritical, transitions like hydraulic jumps, hydraulic losses through our systems, loads on the structure and stability. So of course, scaling is really important for our structures, and it's a real pull between two different constraints. We've got a physical constraints of our laboratory, the physical size of it, the flow rate that we can achieve, or the wave height that we can get in our coastal models, and of course, cost and timeline as well. At the other end, we can only scale down to a certain degree, and it really depends on what we're interested in. We have different scale models. So we might have a harbour model where we're looking at wave transformation. We might be able to do that at 1 in 80 or 1 in 100. If we want to get down and look at the interactions on a coastal structure, it might typically be done at 30 or 40 or 50 scale. Some things like this, what you can see on the screen, these are rock bags. They're bed defense. This we're modeling at 1 in 20 scale so that we can characterize what's happening inside the bag as well as outside. It's important to note that we've got decades of research into the scale effects, which helps us understand how the results translate to the full scale. And of course, sometimes we just can't achieve things in a laboratory, or there might be other cost-effective solutions. So we have quite a number of people that come to us looking to do physical modeling, and we actually talk them out of it and say, provide them other engineering solutions that they can use to get an answer to their problem. Sometimes we do things at multiple scales. So this is a fish ladder. It provides connectivity between different parts of a river, allowing providing that connectivity between ecosystems. On the left is a 1 to 2 scale model. And here we have our instruments can get right down in between and characterize the flows between those blocks really well. This is an ADV, gives us lots of good quality 3D high frequency data. And we can use this to make sure that our broader scale model, which is at 1 in 5 scale, is operating correctly. But this then gives us a chance to look at other things like how it integrates in with resting pools and other features of the structure. I hope I haven't been talking down numerical modeling. I think numerical modeling is a fantastic tool and it's used extensively, and I really support it. For really high risk projects like dams, for example, where you've got an opportunity or where there's a risk for a community downstream, we really strongly recommend hybrid modeling. And it is used quite a lot in areas like dam design. This allows us to compare the physical and the numerical model. We get benefit from both of those. Key challenge for us, particularly with things like aeration, and there's other processes as well that are hard to achieve. They're really challenging for physical modeling and for numerical modeling. Okay, and so one of the challenges that we have is that we don't have really good prototype information. So you think about a dam, which is, you know, designed for maybe up to 100,000 year or a million year event. The chances of seeing that are very rare. And if we even, to capture that, we have to have our instruments in the structure over a very long period. We've got to make sure that they're operating over decades and then that they survive during those very large events. So some things, like loading on a dam structure, it's really hard to get information about things on what's happening at the prototype scale. So we need to allow for that. So here's an example where of a coastal model. We've got our wave paddle offshore generating a wave climate into shallow water region and into our model structure. Got a numerical modeling, is typically done early on, gives us some early design information about our structure, and then we get commissioned as physical models to give more confidence in those results that they're getting on their structure. So there's this region here where we've got an overlap. This is a model boundary for our physical model, our offshore boundary, and we're allowing that wave to transform through here. Quite often we find that the numerical model will overestimate the wave climate down here. Okay, so if we tried to match that wave climate here in the near shore by increasing our wave height from offshore, we find that we get a lot of wave breaking, which causes, a really messy wave condition. We get a transformation in our periods as well, and it's really just unrealistic. So what we need to ensure in a situation like this is that our physical model has a distinct boundary, and we allow the physical model to provide that transformation into the near shore. Similarly, this is a situation for scour protection. So this might be a quay wall. It's part of a harbour. There's scour protection near the toe of the structure to make sure that it doesn't get undermined by ship thrusts. This is really an increasing problem that we're seeing around the world as ships are increasingly using azipods and bow thrusters instead of having tugs to move them about. If we use for our physical modeling, we want to take the power from our thrusters and allow that to project across our structure. Because the thrusters are rotating and, because they've got that vorticity in the flow, they tend to meander. The jet tends to meander around and is really quite a complex flow condition. And that's really hard to reproduce in the numerical model. I'm just going to skip over construction and touch on instrumentation. One of the key things with instrumentation is that we need to make sure that we fully understand our flow condition before we take a measurement. This is what's called an induction current meter. It's got a little impeller here that spins around. The faster it spins, obviously, the higher the flow. In the past, we've seen people using these, and this here is underneath highly aerated flows, so you can't actually see what's happening at the bed. This instrument will give us a result, but you can see with this flow vane here that it's swinging around back and forth wildly around here. So we can clearly see that the flow conditions are so complex here that we can't take a measurement point. It's just not realistic. It is valuable information. We know something about what's going on in those flows. We know it's highly turbulent, it's switching back and forth. So this is located just downstream of an end seal, so in a place of a back roller recirculation. The other point I'd like to make about instrumentation is that it's not static. It's constantly evolving and changing. We've been doing quite a lot of work recently using a dual tip conductivity probe. This gives us really valuable velocity information in highly aerated flows. Similarly, we've been using a 2D LiDAR to measure the water surface. This gives us a really good high frequency data about a cross-section of the water surface. Really good for hydraulic jumps. I mentioned before that sometimes we get surprises, and this is where a physical model is really good for identifying things that we don't understand or that we might not expect to happen in structure. So this here is a situation where we have shallow water and we've got waves approaching a dredge channel. So along this line here is the edge of a dredge channel. And this is analogous to total internal reflection of light. So this would be like if we're in water and we've got an air boundary and light reflects off the edge. Now that's quite well known, but a lesser known feature is that if the approach angle is very shallow, it doesn't actually reflect away. It just interacts with the incoming wave, builds up, and in this case, we have wave breaking. And part of the reason why we study and set up this is that we could see there were observations of the wave condition there which indicated that something strange was happening, but we didn't know what exactly that was. And so this was a really good way of being able to identify that unusual phenomena. Another important factor which we can pick up in physical models quite well is changes in hydraulic conditions. So pipe flow is very sensitive to the tar water or the entrance and the exit conditions, and it can change the flow conditions within our pipes quite dramatically. You can see here a very small change in flow rate is giving quite a dramatically different condition here. So this is a really complex stormwater junction. We've got flows coming down in two pipes that are getting split into three pipes. We've got another couple of inlets here on the sides as well. So quite complex flow conditions. If you don't characterize that correctly, you might underestimate the amount of hydraulic loss through this system and end up with flooding, backwater effects here, providing flooding, overland flooding. Another similar kind of transition between flow cases is this stilling basin here in a dam. So we've got flows coming down our dam, go into this hydraulic jump, which is very effective at dissipating energy. And as you see the flows increase, and this is not a large increase in flows, small increase in flows, can change this. So you transition from a hydraulic jump, and you'll see this go into sweep out. And so here, the loading on the baffle blocks is much stronger. We've got potential for uplift on the slab elements here, and also you've got this quite dramatic plunging jet down here, which is a real strong scar potential. So again, if we have a transition in flows and when we're not able to capture, we have this transition in flow conditions, which provides a dramatically different load case for our structure, and we need to be able to capture that, and a physical model does that very well. So I feel we're running out of time, so I might just skip over that one. The other thing that I will say about physical modeling is it gives a real opportunity for different stakeholders in our structure to come to a common understanding. Here we've got the dam designers, we've got the dam owners and operators, we've got the safety regulator, we've got fish passage experts, we've got other experts as well. You can have people with really different interpretations or ideas of how a structure might operate. You get them together around a physical model, and all of a sudden everyone's talking the same language. They understand the issues, they understand the solutions really clearly. And I think that's a real strong case for using physical modeling, is that ability to communicate the problems and solutions for a structure. I'll leave it there. I think I'm running over time, so I'll leave it at that point there.
Oh, no, thanks, Ben, for that. I think we can, see the summary there of what you've talked about. And we'd encourage any of you in the background who've been watching this to put your questions into the Q&A line. Morten, if you want to turn your camera back on, we'll have a few minutes now to address any questions from the audience that you'd like to hit. And Ben, then if you can have a look and see if anything else that you'd want to hit live. I really like this concept that you mentioned, Morten, here called the Kramer sphere. So the Kramer sphere, you'll have some links to some of those resources in the background. And so I guess I wanted to just, turn it over to you and see if there's anything that you've addressed in the background that you wanted to share with the audience.
Yeah, that is a very interesting discussion started by Rudy van Dry. It's a question about surface roughness effects at different scales and how to interpret the vortices. These effects are not correctly represented by the Froude scaling. So the scaling effects have been studied using experiments at different scales. And it's a problem when we do the Froude scaling that we are not representing all the model properties correctly. So that such effects can be studied by doing either experiments at different scales or with the recent developments in all the CFD modeling to do CFD calculations at increasing scales and see the effects of that. What I very often do when I do experiments is that I try to make the model properties such that they reflect how the calculations are done. So if the calculations on your is done with a rigid model, then I also try to model to make the model, the physical model, as rigid as possible. So there are several things you need to consider, because if you build a larger scale model, then it's more expensive and more time consuming, and it does not necessarily provide more accurate results. So it's very important that you consider the physics that are in play in the experiments and choose the appropriate scaling to ensure that the results are useful for a given purpose.
Thanks for that. I think that's very well said. And I think we've also got a question here for Ben about coastal modeling. Before we dive into that question, though, I'll just quickly share a few things on my screen. Where there's a lot of additional information. I mean, Ben and Morten and many others who could have joined us today, would have hours of presentation material that we could share with you. We want to hit the highlights, but also provide you with any resources for those looking for a deeper dive. So I've set up this additional website here called hydroschool.org/physical, and we've got Ben in our tour here of his facility during the FMA conference. And what we'll also see here on these resources are some of the background materials where you can get some additional content about the Friends of the Mississippi River Basin model, for example. And for that one, you may also want to just zoom in and have a look there. You can actually get, I think there's a Google 360 view that'll take you around to what it looks like today. If you want a little bit of a history of that, you can actually spin around here yourself and take your own little virtual tour of it. We've also got a bunch of free previous AWS webinars that have involved physical models, which is why we wanted to bring this content to you today and get a little deeper into the technical dive. We keep talking about it. Hey, these are really cool, but how do you use them? How do you actually scale them up? So I've just got a few of these resources here, which are available on that website. Some of our previous webinars where we've covered all sorts of things, including how to make your own physical model on a 3D printer. And then if you want to know some background about the Froude number, roughness coefficients and things like that, we've got plenty of first principles. And then if you want a really cool intro into the Mississippi River Basin model, have a look at Grady Hillhouse's Practical Engineering channel here, where he's got a video about this. And he joined us actually and demonstrated to us on a Australian Water School webinar, the concept of stream tables and how it helps with geomorphology. So what I'm going to do now is just in the background while we're talking, you'll see a little virtual tour, worldwide global tour of some really cool hydraulics labs. These will just be slides running in the background. Ben, somebody asked in the background on the Q&A line about utilizing physical models for the impacts of coastal engineering on beach morphology. Anything you'd like to say about that?
Yes, you can, depending on the situation. It's very challenging though. The problem is that you're trying to match you've got to scale the fall velocity of the sediment. And once you do that, you end up with such light sediment that it just wants to float. Okay, and so then you've got to add surfactant. Some cases, the thing it really doesn't do very well is the cross shore. So, you know, if you're standing on the beach looking out, it doesn't get the slope very well. You can do, I had a model that worked exceptionally well where we got the plan form. We were able to characterize the sediment movement on the plan form. And in that we used like a really lightweight plastic and allowed it to shape. So what it's doing is the beach is responding to the action of the wave. Okay, so that, you know, the energy profile of the wave. And then after the structure was put in, I went back and I had a look and I reprofiled it and it worked. It was almost spot on. So it is possible, but it's often just very particular scenarios and can be really challenging.
Oh, great. Now and you'll see all these different types of hydraulic models and all these different types of physical models. They each have their own unique challenges, whether it's coastal, whether it's fish passage, whether it's, we were showing some in some of our previous webinars, we've got some for tailings dam breaches and how to get to debris and non-Newtonian fluids and things like that. All sorts of things you can do with physical models. Morten, back over to you. We've just got a couple of minutes left here. Are there any other questions you wanted to hit before we wrap things up today?
Yeah, there's a question related to uncertainty. How we assess the uncertainty on measurements in experiments, and it's very important that when we do physical experiments that we know all the uncertainties that are involved. We consider different sources of uncertainties. They are normally divided into random and systematic uncertainties. And when we do tests, we do repeatability studies for all the measurements to assess the experimental uncertainty. And all these different uncertainty parts, they are added up using statistical methods, using standard deviation. And as an outcome of that, we get a so-called confidence interval on the measurements. And this interval is needed for comparison studies with numerical models, and also to know what are the limitations of what we are guessing. So if we are after extreme forces, there's another question related to that. Then we need to take the upper part of this confidence interval to get the worst situation. If you want to know a little bit more about this, you can have a look at the supporting material for the event, where there's this paper about the sphere, where it's explained how this confidence interval is calculated for the sphere case.
Perfect. Yes, and that one is available at that website to download directly. The PDF file is available for you there. So, boy, this is it's really cool stuff. I actually, until I saw Morten's Lego model on a YouTube video, we got links to his own YouTube videos on that website, and really seeing this 1 to 50 scale and how the square root of 50 in the Froude number equation gives you the factor of 7 for time. I wouldn't have known if I was filming my own Lego movie, my own Lego film. I wouldn't have known that you can actually figure out how much to change the time to give it a realistic approach. If your basin is the same size and same scale for your my spaceman minifigure here. Ben, any closing remarks that you'd like to share with the audience today?
Thank you, everyone, for joining and signing in and listening. Happy to talk. It's always worth contacting your laboratory, and I would highly recommend getting in touch early. It can be a real key part of your design process. We often see people just come right at the end and they just want to validate, and confirm, and then they're going to be surprised, right? It's really important to come early and engage and include us in the design process. Really.
And if you're going to be in Sydney,
and
come for a visit.
Sydney's fantastic.
Take a tour.
Yeah, come and touch base.
Find one of the open days, yes, and come take a tour. It was fascinating. I got to go along on one of those tours a year or two back, and it's absolutely fascinating. So thanks so much for that. You'll see a few more background resources on some upcoming Australian Water School events. We've got a really busy October. We're trying to fit as much as we can in because we do take a break around the December-January timeframe. So have a look at some of the resources coming up. We'll get to see some of the evidence of the Earth's biggest floods. We've got individual software developers sharing their innovative tools with us. And we've got all sorts of courses with AI and Python scripting and even eDNA, where you get to send in your own sample to get your own analysis done on a water course in your area. Lots of exciting things coming up. So glad you were able to join us today. Do fill out the poll on the way out, your exit poll. Let us know what you want to see more of. And we'll hope to keep bringing you some relevant content for your water career, your career in water resources. And we are so glad we get to be part of that journey with you. Thanks so much for joining us today. Thanks to our presenters, Ben and Morten. Glad to have you with us today. Thanks for all that material. We'll see you next time with the Australian Water School. Bye-bye.